Welcome, everyone. Good afternoon, and I should say good morning in the US, because our speaker today is from the US. And we are pleased to announce Professor Mette Gaarde. She is going to talk today about solids in strong fields. And she is the Les Endot Broussard Alumni Professor of Physics at Louisiana State University. She received her PhD from Copenhagen University in Denmark, with much of her graduate and postdoctoral work performed at Lund University in Sweden. In fact, she worked very closely with Anne-Louis Lier many years ago. She's a fellow of both the APS and the USA and is currently serving as vice chair of APS DAMOP. So we are really pleased also about the number of women that we have managed to obtain to talk in our seminar series. We're very thankful for that. And they are very distinguished people who are giving talks, and women. So we do have a lot of women in our field who are doing amazing work. And she will talk about real space picture of high harmonic generation solids and the role of imperfect recollisions. So thank you so much, Mette, for joining this. And thank you all of you watching. So the floor is yours, and feel free to start.
Okay, well, thank you very much. Thank you for the very nice introduction, and thank you for the invitation. I look forward to joining this again as a participant. I saw that you have a very nice list of speakers lined up, so that's wonderful. So yes, I'm going to talk about high harmonic generation in solids, and in particular, sort of a real space picture, imperfect recollisions, and I will tell you about what I mean by that. And so the work I am talking about today, so here I'm showing you the ultrafast AMO group at LSU. So there's quite many of us, 3 professors, 4 postdocs, 1 PhD student, a couple undergraduate students. And the work that I'll be showing you was really done by postdoc Lu, who has been with me for about 2.5 years, and has been just amazing. And a lot of what I'm showing you is what he has developed and what we have thought about over the last 18 months or so. So maybe it's not necessary to give you a motivation for why you should care about high harmonic generation in solids, but so just briefly, in the last decade or so, there has been a huge amount of interest in harmonic generation in solids. And so early on, and still ongoing, very fundamental interest. How does it work? What are the processes? Interband, intraband, what do the harmonics look like? What's the effect of macroscopic propagation, etc. But now also a lot of work is done sort of with, I would say, two slightly different interests. One is to use harmonics as a spectroscopy source, just like harmonics in the gas phase. So there has been a lot of work on so thinking about probing the structure of something from what the harmonics look like, looking at topological systems, looking for topological effect and how that manifests in the harmonics, phase transitions. So that's one aspect, harmonic spectroscopy. And then of course also sort of harmonics on a chip, right? You have a solid, which is a compact material that where the structure is what it is. It doesn't move, it doesn't change. And so in principle, you can exert a lot of control over your material, and so also control over the emitted light. So for instance, how, depending on what the symmetry of your crystal is, what does the light look like? What is the orientation dependence? What if you dope it? What about elliptically? Can you make elliptically polarized light, et cetera, et cetera? So a lot of work being done on that. And so what am I going to talk about today? So I'm going to start with a brief introduction to a couple of different sort of three-step pictures of solid state high harmonic generation. Both talk about in reciprocal space, so momentum space. and then also in real space, and talk about how to understand all of these 3 steps. How does the laser field interact with the dynamics imposed by the band structure? And then I will specifically talk about what happens if you have not just a 1D system, but a 2 or 3D systems, and that's where you can get imperfect recollisions. So imperfect recollisions is, what do I mean by that? So in space, so here is a schematic. In space, you have the electron and the hole, they are being pulled apart. And then when they come back together, an imperfect recollision is when they don't, when the center of the electron and hole wave packet don't exactly overlap, but you can in fact still get rescattering. And so you can still get harmonics. And so this is what I mean by an imperfect recollision. And so I'm going to talk about when to expect them. And I'm going to give you 2 different examples of that for a 2D system, HBN, and for a 3D bulk system. And also talk about what is sort of the effect of the imperfect recollisions and what can we expect. And toward the end, I will talk about how you can understand the imperfect recollisions in terms of how delocalized the real space wave packet of the electron and hole is. And let me try and get my my laser pointer. There we go. Okay. All right, so let's start by the 3-step picture in momentum space. So if anybody is not familiar with momentum space, it's simply so you have a crystal is a periodic structure in space that also makes it a periodic structure in reciprocal space, momentum space. And so the band structure is simply, for each of my crystal momenta, I solve a time-independent Schrodinger equation, and I have a set of eigenvalues. These are my energy levels. And then when I put all of those together, then I see that my energies vary as a function of K. And so this is what maps out the bands. So usually we think of things simply in terms of the valence band, which is generally fully occupied, and the conduction band, which is generally empty. Okay, so in momentum space, my 3 steps are tunnel ionization from the valence band to the conduction band. Then what the laser field does, the vector potential is simply gives momentum to the electron and to the hole. And so the electron and the hole follow each other in momentum space with the vector potential. And then, and so they are moving up and down the band structure. And then you can have these 2 different kinds of radiation. So the intraband radiation that comes from the fact that the charges are being accelerated on the curved bands. And you have interband radiation, which really comes from the recollision or the recombination of the electron with its hole. You can think of this in terms of a current, and this in terms of a polarization, very much like gas phase harmonic generation. So this is very simple to understand. The dynamics simply follows the vector potential, and I can think of a time-dependent momentum being whatever momentum I started with, plus the time-dependent vector potential, and then I have to sum the contribution from all of the different Ks in the first Brownian zone. In real space, I can also think about these 3 different steps. So again, the tunneling step, now I am creating an electron-hole pair. Then in the laser field, they are pulled apart because they are they move in opposite directions. And then if they re-encounter each other, then I have again a here I have an actual recollision, and I can get emission of the of excess kinetic energy, again very much like gas phase harmonic generation. And here again I can have intraband radiation, which is simply the radiation I get from accelerating these charges in the field. Now, it is actually a bit more complicated to think about the real space picture, because in a solid, as opposed to the gas phase harmonic, my electron is not free once I have separated it from the hole, because it is still bound by dispersion relations that are imposed by the band structure. So to think about where the electron goes in real space, I have to think kind of in two steps. First, what is the momentum that the electron gets from the vector potential? And then now I know where I am in k-space. Now I will have a certain dispersion. I will have a certain group velocity that comes from simply the band structure. And so especially in a 2D system, as I will show you in a minute, the electron does not necessarily follow the direction of the field. And then of course, this is the Berry curvature that can also change the direction of where the electron moves. So these simple pictures, I'm not going to spend very much time on this, but these simple pictures can explain a lot of observations. So for instance, as an example, you're all aware that if there are multiple conduction bands, for instance, that are excited. So if you look at the example down low here, so this is magnesium oxide. Here is my valence band. And there are actually two conduction bands that often play a role. So there's the lowest lying conduction band, and then there's one that sits just a little bit higher. And if I look in the harmonic spectrum, so this is frequency in this direction, then you see that I have harmonics. I have one plateau and then a second plateau, and these can be ascribed to the excitation to the first conduction band, and then that I actually, I don't have enough energies available to me in the first conduction band, because the maximum harmonic energy I can get comes from the maximum separation between the maximum band gap between the conduction band and the valence band. And I should say this was an experiment that was done by Shambu Gamir's group at SLAC. And this was a collaboration we had with them at the time. Okay, so we understand a lot, but obviously there's still many things that we don't understand. So for instance, if you think about the subcycle time profile, so this would control what the solid state harmonics look like in the sort of attosecond domain, or at least few femtosecond domain. Is there a generic behavior? I would claim there is not, and also a couple of different types of behaviors have been measured. And then maybe more coming back to sort of using harmonics for spectroscopy. These kind of all optical probing relies on having a particular model in mind for the harmonic generation process. So, and as I said, especially the real space picture is more complicated in 2D and 3D. So let's take a look at that. So let me just give you a 2D example here, and I will come back to this later. So there's probably too many details on here, but the example that I'm showing you here is for a 2D material called hexagonal boron nitride, HBN. And what I'm showing you here is the band structure, or it is the band gap rather, between the valence and conduction band. And so what's special about 2D materials is that the band gap is actually lowest in this kind of hexagonal structure that sits around the gamma point. So gamma point has the largest band gap, and the smallest band gap is at this K point. And actually also the M points that are here also have pretty small band gaps. And it turns out that the high order harmonics are dominated by tunneling of the electron at the M points. And so what we have found was that when we look at the real space dynamics of the electron that tunnels at the M points, we get precisely imperfect recollisions, as in the electron and hole don't return to the origin. So when the dashed lines here are showing this is where the electron originates, then it goes out that way, and then it comes back this way. And where the little dot is, that's where the so-called recollision is. The hole is shown over here. And what's really hard to get your head around is that this happens with a vector potential that's in that direction here. So you can see how the electron does not follow the direction of the vector potential. And so why is that? It's really because of, like I said, the electron is not free. when it has tunneled, it is still bound by the band structure. It has to obey the dispersion relations that are imposed by the band structure. And so this looks complicated, but here again, now I'm showing you the group velocity for the electron, again in HBN. So here I have the M point. And now look at where so what happens when the vector potential turns on. So in K space, the electron is pulled down this way. And now you see that my arrows here show me the direction of its actual velocity. So that's what's happening here, that in real space, it starts to follow these velocities here. And then as it comes back the other way, it starts to go down this way. And so because in this case, the vector potential is not parallel to the group velocities, then I can get this kind of skewing of the trajectory. Of course, if I had a strong Berry curvature, which generally leads to sort of, it's like little vortices, then my electron trajectory could also get distorted, even if my group velocity and the vector potential were in the same direction. So here, as I said, in real space, I really do have to think about a two-stage process where first I think about which K does my vector potential give me, and then once I have that K, what is my group velocity, and then also what would the Berry curvature do? Okay. Okay, so now I'm going to go on to show you some actual examples of calculations that we have done, and then we will talk a bit more specifically. So just very briefly, how do you do a calculation of harmonic generation in solids? So I would say there are, again, 3 steps. These steps have nothing to do with the 3-step models, but so you need a band structure. So you need to know the your basis in some sense, and so you can do that if you know the potential. You can and you know how to find how to solve that time independent equation. You can do it yourself. You can also use a model, or you can get the band structure from some kind of commercial package. And so by band structure, in general, what we mean is that you get the energies of the different bands as a function of K. And you also get the transition matrix elements. So generally, if you use a package, then what you get are the matrix element of the momentum operator. And I will show you that often we also need the matrix elements of the dipole operator, which actually are not always so easy to get. So, okay, so now you have your band structure. Now you need to solve some kind of dynamics equation, and we use the semiconductor block equations, which is very standard. And here they are written in the so-called moving frame. Again, thinking about this dynamics of the electron basically follows the vector potential, gives it momentum, and so you can also solve your equations in that frame. And in that frame, you need the matrix elements of the dipole operator. And so some of them you can calculate easily from the P matrix elements, but the diagonal elements, the so-called Berry connection, is harder. And so one of the things that Loon did for this project was he figured out how to calculate these in the length gauge by using the so-called twisted parallel transport gauge. So basically you need, in order to be able to calculate this derivative here, you need smooth and periodic block functions, which you are not in general guaranteed to have. And so he figured out how to do that using the stuff that's already in the literature. Right, in the length gauge, also what's nice about the length gauge is that you can impose a dephasing from electron-electron correlation or electron-phonon correlation, and that's it is put in by hand, but it's pretty standard to do so. We have been using about 5 femtoseconds, but for what I'm showing you, it's not going to matter a whole lot. Our results have been robust in this regime between about a few and up to about 20 femtoseconds. Okay, so band structure, now you solve the dynamics, and now once you have the dynamics of your system, you can calculate the current, and if you're working in the length gauge, then you can calculate both the inter and intra-band contribution to the harmonic generation. Most of what I'll be showing you in the next couple of slides were done at 1600 nanometers for a 30 femtosecond pulse and a few terawatts per centimeter squared. Okay, so now I'm showing you some results here. So this is the harmonic spectra for, this is for harmonics parallel to the laser field. This is for harmonics perpendicular to the laser field. And what you see, so again, we are not the first to see this, but when you look at the parallel direction, you see only the odd harmonics. When you look in the perpendicular direction, you see only even harmonics, and you can understand this from the symmetry of the crystal. Now what's shown here, so this is when the laser polarization is in the gamma K direction, which is like this, the red arrow shown there. So what's shown here is the time frequency profile. So you see this is the subcycle emission profile during one half cycle and another half cycle, again, parallel and perpendicular. And what I want you to pay attention to here is that there's kind of a double peak structure. So if I, in gas phase harmonic generation, right, then I would expect something that was like short and long trajectory, right, in the emission profile. And this really looks quite different. First off, as I will show you, these are not really short and long trajectories, even in each of these, but also I have two of them, right? So I have one here and another burst there. And so when we first saw this, we did not understand where these were coming from. And so we tried a number of different things. Are these like super long trajectories that are happening? So we try to decrease our dephasing time, but you see actually even going all the way down to 2 femtoseconds, we still clearly have double peak structures. And so this is not, these are not just something that we can make go away by more aggressively dephasing our calculations. We actually also tried somewhat similar idea. Could we remove them by something reminiscent of phase matching? So we calculated sort of the result, what you would get from having a radial distribution of across a laser focus. Then we went, this is now the spectrum in the far field that comes from that. So we filtered it, we threw away everything that was off axis, and then we transformed back to the near field, and we still had double peaks. So again, this is not like long, like short and long and even longer trajectory. It's something different. So what is it? And so what Loon then did was that he worked on slightly extending the sort of the real space recollision model that was first proposed by Julie Vampa and Thomas Brabeck. And so, I mean, most of you probably are familiar with this, but so what is the 3-step model? Well, we have 3 saddle point equations that basically say you tunnel at time s with a certain momentum, then you have a recollision at some time later with a different momentum. And what we did slightly differently from what has been done before, we allowed that by the time the electron and hole come back together, they don't have to be on top of each other. So we defined a recollision to be within some distance. Actually, this is the distance of the recollision, but this is almost the same. So so the electron and hole can be separated by some distance, and then we also included we also included, this comes from basically the dipole phase, and which we had included, and then we included the Barie curvature in the calculation of the, so R here is the integral of the velocity, and the velocity is the dispersion coming from the band structure, and then the Barie curvature. And so what's different here? So we allow a recollision that where the electron and hole are separated by some distance, and then because you have a separation at the time of recollision, you get an extra contribution to the energy. So this is normally what you would have. You would simply say that the that at the time of recollision, then you are emitting this frequency, and that corresponds to the instantaneous band gap that the electron is at that time. But now we are adding this extra term that comes from the fact that the electron and hole are separated, and so you have a polarization energy, basically. Okay. And so now what I'm showing you is that on top of the results that I showed you before, I'm now showing you the results of these classical or semi-classical trajectory calculations. And so now for each K point, you can think about if, so for instance, if the electron is released at the M point, either the M1 or M2 point, then what is its time frequency profile? What is the emission profile that that it would give rise to? And that's what you see here in black. And so, whereas from the two K points, we only get lower harmonics. So one thing that we learned from that was that the highest harmonics are definitely driven by the M point electrons. But we also saw that there's no double peaks, right? If we're just looking at the M points, we just get something that actually looks pretty standard, right? This looks, and it is, this looks like short and long trajectory emission, and that is what it is. But we are missing this other peak. So what we then did instead was that we looked not just at the M point, but a range of electrons in a small disk around the two M points. And what we found was that basically within that disk, there is a difference between are you to one side or the other side of that symmetry point, and that gives you two different types of short and long trajectories. Excuse me. And so this is what gives us the double peak, and these are actually separated by almost a full femtosecond. So I mean, it is a substantial shift that you get. And it turns out, oh right, so here they are on top of the numerical results. So we really do believe that that's what's happening here. Also, interestingly, if we don't include that polarization term at the time of recollision in the energy, then we cannot reproduce the two different emission times. We get something that looks different. So that really turns out to matter in this case. And so that really comes from, I should say that it really comes from the fact that that we must have what we call these imperfect recollisions, because if we don't allow for the energy that comes from the electron and hole being separated, then we don't get agreement with the full quantum result. And it turns out, in fact, that when we calculate these trajectories, the imperfect recollisions are quite common. So here are just some examples. So this is from the M1 point. You see that the separation upon recollision is about 5 atomic units. And then from two different points, a little bit away from the M1 point, then we have even actually much bigger separations, right? About 15 atomic units or 20 atomic units. So, and this is to be compared to the fact that the the spacing between atoms, the lattice, I'm sorry, what is it called? Is only a few atomic units. I think it's 3 or 4 atomic units. So these are huge separations between the electron and the hole. So how to think about that. I think I've talked about this already. So I mean, in general, right, why do I get this separation of the electron and the hole upon in the 2 or 3D motion that they undergo in the crystals? And this comes from the fact that that when I have my electric field not parallel to the group velocity, or more generally, I could have a large Berry curvature, I could have elliptical polarization, even if I did have something where the field and the group velocity were parallel. So, and actually, in fact, we found that when we look in a different direction, if we go in this direction, now the A field and the group velocities are parallel, and so indeed we don't get a double peak in that case. So double peak created by the imperfect recollisions. Let me just show you briefly. This is for a slightly different system. So this is a bulk now. This is zinc oxide, and here we were doing exactly what I talked about just before. Used elliptical polarization, and so now what am I showing you here is the band gap. So it has the same symmetry as HBN, but what's different about zinc oxide now is that the gamma point is where the minimum band gap is. And so what that does is that if you're always tunneling from the gamma point, then at least in linear polarization, the group velocity is always parallel to the field. And so in linear polarization, you don't have any imperfect recollisions. Also, the Berry curvature is small in zinc oxide. But things are very different when you look at elliptical polarization. And so here, for instance, you can see the spectra also look quite exotic when you go to towards circular polarization. So here is spectrum as a function of ellipticity. And you can see that whereas at linear polarization looks like any harmonic spectrum, but then as you go to circular polarization, you see you actually have something that's where you have kind of a hole, and then or a dip, and then the harmonics kind of revive as you go toward the cutoff. And I will show you that we can understand this in terms of, again, of the imperfect recollisions. If we look at the time frequency profiles in zinc oxide, we get 3 wildly different behaviors for linear polarization. This now looks pretty similar to what I showed you before. And then elliptical polarization, and then circular polarization. So where do all these kind of exotic time frequency behaviors come from? And so interestingly enough, that if we only allow tunneling from the gamma point, then the only thing that we can reproduce of this is this behavior at for linear polarization. We can't see any of the behaviors for the elliptical or circular polarization. That simply is not driven by the gamma point electrons. But now if we allow tunneling from a disk, so we expand a little bit away from the gamma point, now you see not only do we get this sort of interesting boot structure, that's what's sitting up here, and then as we go to elliptical and circular polarization, this boot structure becomes this whole triangular structure, and then that repeats itself many, many times. And so we looked at, we as in Loon did all of this work, and so he looked at now which of my K points in the Brion zone contribute to which harmonics. So these are now color coded. So this is the Brion zone, and these are now color coded. So for instance, out here you see that the the highest energies at linear polarization, it's sort of turquoise, they come from maybe even from the gamma point itself. Whereas if you go to elliptical polarization, now the highest energy is this point here. It comes from a point that's away from the gamma point. And then as I go to circular polarization, you see I actually have to go only electrons that are relatively far away from the gamma point contribute to my harmonics. So I think it's a nice representation of how you really have to think of your solid as not just one type of electron that starts with one type of momentum. You really can get very different behavior depending on which part of the Brion zone that you start from, and especially once you go away from linear polarization, that all of those electrons really matter. So that's really a lot richer than for harmonic generation in gases. Now I'm really talking in the weeds here, but we have also looked at what do those trajectories look like. And for instance, they correspond to a Bragg reflection where the electron goes to the edge of the Brion zone and then is turned around and comes back. Okay, so the last thing that I wanted to talk about was we wanted to try and look at not just the classical or semi-classical trajectories, but also to think about how do we understand this kind of, why is it allowed that the electron and the hole are so far apart when they re-encounter each other? Why do I still get harmonics from that? And so this really has to do with how incredibly large the real space wave packet is. And so let me just move on to that. What Loon then did was make an attempt at constructing this this real space wave packet. And so this requires expanding the wave function. So we used the Houston states, which are really just like the states in the moving frame. And then also you have to make a guess at what is the initial distribution of K points in order to make your initial wave packet. And so he estimated, so this is back to HBN, by the way, I should say that. He estimated from kind of tunneling probabilities. So we know that the highest harmonics are dominated by the M-point electrons. So we did a small range of K points around the M-point. And then we made a 2D structure out of that. And so then what you get is, so this is the initial wave packet here. And you can see both so each of the little dots, that's, no, I think there are 6 little dots to one lattice cell. But then you can see the hexagonal structure, and you can see how incredibly large the real space wave packet is. And so already, once you see that, right, it makes sense that that these separations of even tens of atomic units at the time of recollision, that can still lead to harmonics, because you still have some overlap between your electron and hole wave functions. And so then he calculated, if you compare the semi-classical trajectory, that's the orange points, and then follow the center of the quantum wave packet trajectory. And we could also, if you plot the spread, basically the full width half maximum of the wave packet, then you see that it's huge, right? It starts out at around 40 atomic units, and it spreads to about 50. And I have actually a movie of that on the next slide. So let me do that. So here I'm showing you the real space wave packet for the electron and for the whole wave functions. And so this is for the endpoint. And so you will see this marks time and the vector potential, and then you see how the wave packet moves. Let me see if I can do that again. There we go. And so in this case, as I said, this is one of the smallest separations upon return. This is about 5 atomic units, but you see that even 10 and 20 atomic units are well within the size of this wave packet. So that's how we understand we understand this kind of overlap between that the imperfect recollision can still give rise to harmonics upon return. Okay, so I'm almost done. And I think that I just wanted to sort of say, now I showed you a lot of details, but to think about what might this mean? So the fact that the wave packet is so large. So one thing to think about is that it probably decreases the sensitivity to ellipticity, right? And that has definitely also been measured in experiments. The idea that, you know, in the gas phase, if you have elliptically polarized light, we all know this, the electron goes out and then it misses upon coming back. And so, but now when the wave packet is so big, then missing is simply not as bad. So you would expect a different sensitivity to ellipticity than for gas phase harmonics. I think something that's really interesting to think about is, in my opinion, this would increase the sensitivity to impurities in the crystal, right? Because now both your wave packet is large, and it has to go, far away from where it started. And so I think you would be quite sensitive to that there were imperfections in your crystal. And something to wonder is maybe most calculations, at least, and I mentioned this briefly, introduce some kind of temporal dephasing by hand. I think it's very interesting to think about whether some of this temporal dephasing is really, in fact, spatial dephasing, that you lose the coherence between the electron and whole wave packet because you're interacting with these small spatial imperfections. There has definitely been some work on thinking about impurities, and there's of course also a lot of work thinking about where does the rapid dephasing come from. Thinking about size, right? As you go from the size of a molecule to a nanostructure to a solid, when is something big enough to support this very extended wave function? When do you reach the limit of the solid? Again, there's work being done on that, so very interesting. Also, I should say that this kind of thinking about the imperfect recollision, the size of the wave packet, we are not the first to do that. There have been some thoughts about this in the context of high order terahertz sideband generation. Also, there has been work on this using the Vanier picture of harmonic generation, and also thinking about the spatial, both size and localization of the wave packet. So those are similarities to what I've been talking about. And I think I will skip this because I have already talked to you about a lot of details. And this is another detail. I'm happy to answer questions about it. And so let me just finish off again by saying that this work was really, really driven by my postdoc, Lunyu, who has been just incredible. Very impressed by everything that he has accomplished. Some of the earlier contributions to this work, so Mengxi Wu was originally a PhD student at LSU, then was a postdoc, so he developed some of the very early work that we did in this field. a couple of my colleagues were involved, and we were very grateful for the experimental collaboration that we had with the Reese and Gimir group at SLAC. And of course, very grateful for the financial support, primarily by NSF, but actually some of what I didn't show you was supported by the Air Force. And then I thank you for your attention. Thank you.
So thank you so much for this amazing talk. I'm really thankful to see how rich the dynamics with solids are, and the amount of things that can be done. So we have quite a lot of questions. Before we start, I would like to make a brief announcement. We have a special issue associated with the Quantum Battles workshop, which took place last year, and the Atto Fridays Seminar Series in European Physical Journal D. The issue is called Quantum Aspects of Auto Science. So if you like to submit, drop us an email. The deadline is today, but some people have been asking to extend. And apart from that, I'm going to start with the questions now.
Okay.
So there are quite a few ones in the chat, and we have some raised hands. If any of you would like later on not to be included in the YouTube video because we are streaming this, drop us an email and we're going to remove it. So the first questions, actually the first 4 questions are from Guillemot Ernot. And the question is, you have considered that electron hole pairs might not recombine when they are on top of each other. However, in all your slides, it seems that the electron hole pairs are always born on the same position. Wouldn't an ionization of set cover your imperfect recollision distance?
I'm sorry, what was the end of the question?
The end was if, hang on. If tunnel ionization offset would not cover the imperfect recollision distance, that there is some offset in tunnel ionization, and if this wouldn't somehow make up for the imperfect recollision distances that you have, from what I understood.
Okay, is this in the chat or is it in the Q&A?
It's a Q&A. So all the questions are in the Q&A, but I've been asking the participants as well to chat, and I've been doing that. So if they feel like chatting instead, there are quite a lot of questions.
I am not sure that I understand the question. So I mean, in some sense, maybe I could just speak. So we have in general assumed that our electron and hole started in the same place, and I guess we have dealt with the fact that even if they do start in the same position, then they end up not in the same position. And so I am not sure what I'm not sure what your question, if you are there live, maybe you can ask me. And
yeah, maybe that would be nice. I have allowed you in, so you can unmute yourself.
And I try? Oh yeah, I can talk. Hello, very nice talk.
Hey. Oh, good.
Let me try to rephrase the question if it's not as clear. So what I understand is at recombination, electron hole pairs are not the same position, and you need to account for that and the polarization that is built up from that to map. My question is, wouldn't you be able to cover that missing distance between the electron and hole with some tunnel ionization that wouldn't lead you to tunneling at the same position? That is, you leave your hole where it was, but your electron was born delta R away, and that would lead to a different energy time structure also.
Yeah, I think it would, although that's not usually how, I mean, that's not usually what you do in this semi-classical model, right? I mean, you assume that they start in, so in some sense, you're saying if I changed my semi-classical model in a different way, right? If I allowed for a separation at the time of birth rather than at the time of recollision, I would get something similar. So I think I believe that.
I believe the complete answer would be like both, probably.
Yeah, sure. Yes. Right. And I guess that my point was more about that, because we're interested in the dynamics that ensues, then that's where you see both the effect of the laser field and of the dynamics that's imposed by the band structure itself. And so in some sense, that aspect of it is the same, right? I mean, whether you start slightly apart or on top of each other, you would still experience this kind of, you would still experience both kinds of dynamics. So I agree with you. Interesting question.
I have also a few raised hands and another questions from him as well. So I'll let, so to continue, you were also asking, Guillermo, about your wave packet in real space, that you had to Fourier transform your K-space block wave packet. Is it picture strongly dependent on what you call the structure gauge, the twisted parallel transport gauge? A different structure gauge would give you a different spread of the wave packet. How far is the gauge from the Fourier limited transformation, or I believe equivalently to the maximally localized Vanier state?
Right, so I think I will answer a slightly different question because in some sense, let me go back here. There. So the initial size of our wave packet does not depend on the gauge so much, but it does depend on what we choose as the initial bandwidth in K-space, right? As you're kind of getting into with the end of your question. And so we tried a couple different things. So in one direction, if you, I don't know, I don't want to find a different slide, but in one direction, in K-space, it's actually pretty easy to see how big your wave packet should be because we looked at tunneling probabilities, and because there's only a narrow strip in the Brion zone where the band gap is small, and so you can estimate pretty well what is the probability in that direction across the endpoint. And so the other direction is trickier because this is sort of going between the two K points. And so we tried a couple of different widths in K-space, and we found very little sensitivity to this. I mean, of course, you can go to an extreme and really, really change the size, but we tried a couple different sizes, and we did not get a huge difference in sort of in the size and the behavior of the wave packet when we did that.
Yeah. I kind of disagree with your first statement. Let's see if we can find a common ground. When you say, I understand, so for the way I understand it, you're doing a Fourier transform. And we are all in ultra-fast science here, and we all know that for a laser pulse, we need to take all the colors, make them all in phase, and when we add it up, this is when we have the shortest pulse in time. Similarly here, you're adding up all these block states in K-space.
Okay. I understand what I mean. Yeah, you can't do it unless you're not in the twisted parallel transport case. I mean, you can't do it unless you have smoothed out the phases.
Okay, but the phase can be smooth, but still have a quadratic dependence. So how far is that gauge from what I would call Fourier limited, or like? And I think the equivalent description is maximally localized Vanier. But
right, I'm not sure I know the answer to your question. I mean, it's not just smooth, right? It's also periodic.
Yeah, that's twisted parallel.
Yeah, exactly. And so have we imposed a quadratic phase on that? I don't think so, but I don't know the answer to this. I don't know the detailed answer to that. It's an interesting question.
Okay, we had also Hardy Gross who raised his hand. Hardy, welcome to the talk.
Hi.
How are you?
Was basically the same question like the previous one that I wanted to ask. So your basic wave functions are Bloch states. Mm-hmm. So how do you choose actually the size of the initial wave packet?
Right. So I was trying to answer this before. So in some sense, it is a difficult question, right? Because you want to describe the dynamics of a particular part of your wave packet. And so maybe this is also somewhat answering the previous question. I mean, you're not trying to describe the dynamics of the entire wave packet, for instance, right? Because the entire wave packet in time would mostly show you the linear dynamics, right? So you have to isolate a part of your wave packet that you are interested in, the part of the wave packet that gives rise to the highest energy harmonics, right? And so what that means is that in case, so maybe this is also what's answering Guillermo's questions, but I mean, I need to start from, if I only look at the endpoint, then in real space, that is an infinitely broad wave packet, right?
Exactly.
But yeah. And so what I was trying to say here is that how do I have to pick some width in K-space that is representative of what this part of my wave packet does, right? That gives me these highest order harmonics. And so that's what I was saying, that in one direction, if I think about, let me see if I have the band structure. I have lost the ability to do anything with this. Anyway, if I think about in one direction, where I kind of go across where the endpoint is, then I have a pretty narrow distribution of Ks. And so we looked at Zener tunneling, and we simply said we made the K distribution in that direction from the tunneling probability. In the other direction, it is trickier because you can't use Zener tunneling, because, for instance, as you get close to the K point, the probability is even higher, but we know that the K point electrons don't give me the highest harmonic energy. So what we tried was a couple of different widths. So we tried 0.1 atomic unit, 0.2 atomic units, and we did not see a huge difference in the behavior. So I think that answers your question.
Okay, thank you.
Thank you. We have also quite a lot of questions. So Jens Bigard saying, really nice talk and wonderful work, Mette. With the large spatial excursion of the laser-driven electron wave packet, how should I think about carrier scattering? A spatial redistribution, probability density? So
I think you are talking about scattering, like if I imagine that I have a different hole that has been created somewhere, different electron hole pair. And so, I mean, this comes down to how many electron hole pairs do I have, right? And I think we have, I don't remember the exact numbers, but in some sense, the probability of excitation to the conduction band is not that big. And so you don't actually have all that many electron hole pairs that are close to each other. But I guess I would more or less agree with your supposition that yes, it would give you some kind of reduction of so you could treat it like some kind of dephasing again, but we have not done that. It's also an interesting question, sort of more generally, how would you now put this together with the idea of macroscopic response and what does that mean?
So thank you so much, Mette. We have also something from Guillermo Enot. Houston states just look like a length gauge to velocity gauge transformation of the time-dependent block states. Is this definition correct?
Yes, so it's basically the only difference is that there's a phase on them as well.
So that is fine. And there was one question about your elliptical work, also from Not. In your elliptical work, you have a greater cutoff for circular harmonics. Is that a result or a consequence on how you define your electric field? Is the intensity of the two simulations the same?
So what we did was the same. Oh, you're saying that I don't actually remember. I remember that we talked about it, but I mean, if you look at how they compare up here, then I mean, my highest order harmonics are not, no, you're right, they are a little bit higher. And I think you are correct that the intensity is not necessarily the same with the elliptical polarization. We copied for this some work that had been done by a Chinese group a couple of years before. And so just to make sure that we reproduced their spectra, and it's possible that we were not consistent, or I mean, we did what they did, but I think you're right that this this does not preserve the peak intensity.
So are there further questions? Would anybody like to ask anything? We are going to stop the live streaming soon. So if you would like to talk with our speaker, Professor Gaarde, just hang in there if you are a bit shy and if you don't want to be doing it in a very public way. So thank you so much for all of you from YouTube who are watching across the globe. So we're going to stop the recording. We're going to stop the streaming. So thank you for joining and see you soon. And thank you for supporting the initiative.